The third talk is given by Fouzhan Hosseini. I'm sorry for my poor pronunciation. And she's from the NAG Limited. And the title is Meet the POP CoE, Getting Insight into HPC Code Behavior. So, the Fouzhan, is it correct? Fouzhan?
It's Fouzhan. Yeah, Fouzhan.
Fouzhan, okay. Please go ahead.
Yep. Hi, everyone. First, I wanted to thank conference organizers for all their effort in putting a conference together and organizing it in such a nice way and allowing us to interact with each other in this difficult situation. I also want to thank all of you for joining me for this talk. So today I'm going to talk about performance optimization of HPC application code. So most of you probably at some point had to deal with the performance of your code. I'm going to tell you about an approach that we have used over the last couple of years to make this understanding of HPC code behavior more systematic. So I am from NAG. NAG was funded more than 50 years ago from a multidisciplinary venture headquartered in Oxford, UK, but we have become a global SME with offices in the UK, US, EU, and Asia. Over the 50 years, we have become renowned in numerical algorithms and HPC. NAG library is the most rigorous and robust collection of numerical algorithms available, but NAG also offers automatic differentiation, machine learning, mathematical optimization, as well as world-class HPC and HPC consultancy and cloud HPC code porting and optimization, benchmarking, and so on. Over the years, brands such as AMD, ARM, and NVIDIA have relied on our IP, and today we partner with major cloud providers, and also we contribute in publicly funded R&D projects. So one of these projects is the POP project. Performance optimization and productivity, or in short POP, is a center of excellence in HPC funded by EU under Horizon 2020 Research and Innovation Program starting from 2015. It includes 8 commercial and academic partners with excellent track record in programming tools, programming models, performance tools, and vast amount of experience working with various HPC applications. So for this audience, I don't need to convince you that it is good. It's good, very important to write efficient parallel code or to optimize your parallel code. POP exists to promote best practices in parallel programming and help everybody across Europe to better use their computing infrastructures. But what probably you will ask me is like, what is so specific, or what is the approach POP is taking that makes it a bit different? When we want to optimize an HPC application, this usually becomes a trial and error process, and that's because of the complexity of both HPC code and HPC applications. And also, it happens a lot of time that we are not working with the code that we have written and we want to optimize. A lot of time we have to work with legacy code or even codes that was written 10, 20, 30 years ago and for a different area of computation. So that's why, you have a code, as Sunita pointed out in her talk, you have to always start for understanding what is wrong with the performance. But again, that's a very trial and error process. So the problem is usually lack of a quantitative picture of application behavior. And the POP methodology wants to address this using a hierarchical set of performance metrics. So I will get back to this methodology, but first I will tell you about services and work that we do for the HPC users and the community in Europe. So we have a performance assessment services where we analyze the code and make suggestions on how to improve a code for our customers. And we can also provide practical help with code refactoring to customers via our proof of concept services. We also provide training and education. All our services are free for all customers around Europe, UK, EU, and it's open to all domain of science and technology, academic or industry. That this all are covered by our funding. Also, we collaborate with other HPC CoEs funded in EU, also HPC centers. So I touched on the motivation behind the POP methodology. So let's dive into this problem. So we all know understanding performance is very hard. So if we have a code, how do we measure the performance? We can use the speed up and efficiency metrics. And that's useful to give you an overview of the behavior, but it's not that useful in telling you what are the causes of inefficiency. That's why most of the time we use performance monitoring tools. So we can use profiling to get an overview, and profiling can be very useful in spotting the hotspots in the program, but not all the time. The other option is using tracing, so recording events when the program is being executed. Tracing is the most flexible and the most powerful tool because it collects all those information about the program execution, but it can generate overwhelming amount of data, especially if you are, analyzing a code that on the more number of cores that you use, the tracing could, the amount of data that you're collecting will increase. So even with tracing, it can be quite difficult to know where to start in the data and what to look for. So again, this is, because we don't have a quantitative understanding of actual behavior of the application. So a solution to this problem is to use the POP metrics. The idea is simple but very powerful. What if we could devise a simple set of performance metrics which represent common causes of poor performance for power programs, and also they can be calculated very easily from trace data. With such a set of metrics, we could easily see, if we could, with the low values, would guide us on what are the causes, what is causing poor performance for an application, and then with that we kind of have an insight going to the trace data and identifying in more details the reasons or the causes of poor performance, how we can actually improve the code. So here you can see the POP metrics for Mpi Applications. We don't have time to go into detail of how these metrics are defined, but you can see that they are arranged in a hierarchy and at the bottom of the hierarchy you can see metrics that represent common causes of inefficiency. For example, poor IPC scaling or load imbalance or data transfer issues. All of these metrics can easily be calculated from any trace data. So it needs some very basic information like total runtime or average or maximum useful computation time and so on. These metrics have been implemented, calculation of these metrics have been implemented in the open source tools that are being developed by our partners. One example is the BSA, Barcelona Supercomputer set of tools, X-Ray, Power Dynamus, or SCOP, Scala, and Cube. Macro and PyPop also support easy calculation of this automatic calculation of these metrics. But as I said, these are calculating using very basic data from trace data. So for most of the for most tools that you can collect trace data, you calculate these metrics by hand. For example, in some of the assessments that we have done, we've used Intel tools, and because it's a good match for the Intel hardware that we were using, but we could still calculate the POP metrics using these tools. To learn more about these metrics and how you can calculate it, you can visit the POP website. So now let's look at the examples and see how the POP metrics can help us in performance assessment using real examples. So these are all of the examples that I'm giving are from the services that we have done for users around Europe. So the first example is a computational fluid dynamic code. It was a C++ MPI code. And we ran it on 1 to 16 nodes on Marnostrom 4 at BSc. And you can see that on 16 nodes, the performance drops below 80% of ideal performance. Here is the table of POP metrics for this application, again, running on 1 to 16 nodes. The efficiency metrics are defined in a way that the value are between 0 and 1. And as a measure, we say anything above 80% represent something that is good or good enough, because it represents 80% of ideal. So looking at this table, the lower values are shown with red and the higher values shown with green. This table, just looking at this, you can immediately see that serialization is the main factor that limits the scalability of this application. So this is the first insight that you get from the metrics. Then you need to go back to your traces and understand what is causing this. In this case, we were using a Scopy and a Scala. So serialization typically happens when one process arrives late or early in synchronization point. And to understand what is causing this, we could use a Scala delay cost metrics, and we identified that MPI collective calls and imbalance computation region within an MPI call, within a library call, was the main causes of serialization on 16 nodes. So as you can imagine, having that piece of information, that serialization is causing poor performance for this application, was very important and very helpful to do the analysis. The other example is molecular dynamic simulation code. It's a Fortran MPI code with some, it was a legacy Fortran code with some higher level of more recent C++ layer on top. And the code doesn't scale that much. As you can see, it doesn't really scale beyond 8 cores. And for this case, we didn't have access to the source code because it was for industrial user that they couldn't get us access. So the POP metrics in this case, again, shows two factors here: load imbalance and poor instruction scaling, which means increasing instruction counts, as the major factors that limit the scalability of this application. So instruction scaling means that when you have a poor instruction scaling, it means that you are doing more work as you scale up. So you are doing more work, either redundant computation or some work to do manage parallelism. So the pink line here shows the total useful instruction, and we can see that it's increasing as we expect. Also, looking at the average number of useful instructions that are being executed, the blue line, sorry, the difference might not be quite clear here, and the green line shows the instruction executed by one processor. And we can see that as the number of processor MPI ranks used increase, then the processor one is doing more and more work in comparison, and none of those limits the scalability. So in this case, like even not seeing the code, but using the metrics, we kind of understand what's happening in the code. And this helps us in communication with the customer. And it's also very helpful for the customers because they can look at this and then in our conversation with us, they can really understand how what's the implementation is causing poor performance as they scale up. The third example, again, is a computational for dynamic code. It was Fortran OpenMP. And you can see, again, the POP metrics. Here, the MPI related metrics are replaced by metrics that make sense for OpenMP code. Again, looking at this, we can immediately see that IPC is scaling, and poor OpenMP region efficiency causes limits scalability of the code. For this code, again, we didn't have access to the source code, so we did analysis on executable. But the customer was interested to get more help with improving the code. So based on the analysis, we could make some suggestion on how they can possibly improve the code. But sometimes, you know, they are happy for they want us to give them more hand, and we can do that. We are proof of concept. So for this, they gave us a kernel of the code, not the whole code, but a kernel of code. And on the left here, you see the POP metrics for that. And we helped them to modify the code. We modified the code basically using some tricks like using OpenMP collapse and moving some calculation out of the loop and doing some reordering and so on. And you can see on the right that all of these metrics has improved. So both the IPC scaling and OpenMP parallel efficiency metrics improved. So in this case, we worked with the customer. They got improvement. We work on the code, both the sequential code on one thread and also the power code in performance was improved. Also, the scalability of the code improved. But that's not the only thing. The other important thing is that working with this customer, we managed to transfer some knowledge to them that about writing parallel code, which will be useful for them in long run, not just for optimizing this one code. So as I said, POP started in 2015. Since then, we have done many services, more than 350 services across all domain of science and technology, engineering, for example, earth and atmospheric science, biology, genetic, physics, and many other domains. I suggest you to have a look on our success story pages so you can learn a few tricks that might help improve your application as well. The range of speedups that we have achieved is very different and depends on the application, really. So it could be an interesting read for somebody that is generally interested in HPC application and performance, because you see a wide range of issues and different kinds of solutions. We have a lot of online content as well on the POP website. If you want to apply for a service, that's very easy. You can just fill in a form that takes less than 2 minutes. There are a lot of training and educational content. We have blogs, newsletters that you can subscribe or see the past issues. You can see our learning materials and webinars, past webinars, and the upcoming one. We have also the YouTube channel that takes a lot of contains a lot of educational videos. One example is online training that is available for free to everyone. It's a series of self-study modules, short and very short, like 10 to 20 minutes. And that's aimed at people that have limited experience in performance analysis of HPC application. And we hope that we can give them a jump start by teaching them how to use the POP methodology and also some of the open source tools that we are using, for example, X-ray and Scorpius Galaska, and really we start from very basic of how to even install the tool to more advanced topic of to do more tricky analysis for huge trace files, for example. To sum up, in this talk, we have seen the POP methodology and how this methodology uses performance metrics to build a quantitative picture of application behavior. This gives us an initial insight that is very helpful when we want to go and look into trace to understand the performance issues, and also helps us to quickly identify a strategic direction for code refactoring. So you have seen the MPI and OpenMP metrics. We have hybrid metrics. There is a webinar on our page, POP page, about the hybrid metrics. If you're interested, go and see it, watch it. And we are like metrics. We are finalizing metrics for vector operations, I/O, and looking into using accelerators. POP works across all domains, platforms, scales, any programming model, and services open for free. They are for free for all EU, UK-based organization. We are very invested in training HPC users and experts, and we are very open to collaboration, so please get in touch. Also, to end this talk, I'll leave you with some pointers on how to get more information about POP, or on the website or social media. We have an upcoming webinar on end of July, 27th of July, about using X-ray and Power. So if you want to get more familiarity using those tools, just go to our website and register. Thanks again.
So thank you very much for a very interesting talk, Fouzhan. So once Marek made some question about the tools you are using, but you already shown in your slide about tools, for example, Scalaska or something. So he withdraws the question, I think. So another question from Georgios Marco Manoris. So are there any efforts for GPU metrics analysis?
Sorry, can you repeat that?
Are there any efforts for a GPU metrics analysis, not the CPU?
Yes, so we have, yes, there is. So we are discussing them internally at the moment. We have, we are getting more and more applications that use GPUs, obviously, because they have become more common. And then we have done assessments for such applications, but the metrics haven't finalized. So one way you can look at it, so what it will show, basically the metrics, it shows how in the system level the application is behaving. So what are the, it doesn't, to see how well the code uses GPU, you always need to go and use the metrics that is specific to that architecture. But what the POP metrics would show you is like on the system level, how well it scales, like when you're using 1 GPU, 2 GPUs, 3 GPUs, and how that operates with when you have MPI applications. I haven't put it in the slides because they are not finalized yet. So we kind of do application driven, right? Because we have to find the common causes and how the best way to represent those inefficiencies. And the more applications that we work on them, we can better finalize them.
Okay, so this is a question from me, but then. So you mentioned that the EU, UK, the service is free of charge, but do you have any worldwide service with some charge for this POP CoE?
So if it is like training or dissemination and so on, we always like accept people from worldwide. But for doing the services under the terms of the public funding, we can't give it for free. But like we have the expertise, so if people are interested, they can get in touch with us. And for example, NAC can provide the same service, but it doesn't go under the POP, the funding, limited. So it cannot be free. But we can provide the same service. Like actually, NAC, for example, NAC always provide HPC consultancy services.
Okay, thank you very much. So
Thank you.